This is our first video for Module 4 on functional groups and electron movement. So at the end of last module, we had a preview of all the functional groups, not all of them, but the ones of importance for now. These tables from McMurray, I'll point out the ones that we already know, actually. So alkenes, right? Alkynes. So this is one of them, aromatic ring or benzene kind of ring. That's one to remember. I didn't really go into halogens much, but basically if you have a fluorine, chlorine, bromine, iodine attached to carbon, then you pretty much know that that's a functional group. Alcohols, ethers, we want to know. We want to be able to recognize them and begin to understand their chemistry and behavior, their reactivity. These we can skip for now. Phosphates. Amines, though, we definitely want to know about. Imines we can skip for now. Nitriles I mentioned as one good one. That's an sp hybridized functional group. Thiols we want to recognize. Sulfides we want to recognize. These we can skip for now. Aldehydes we want to know. Ketones, carboxylic acids, esters. Amides, we can skip thioesters for now. Acid chlorides, well, those are pretty easy. So, And then anhydrides, which I actually did kind of mention, but again, you can take it or leave it for now. So, one thing to point out, notice that all of these, notice that all of these have a C double bond O group, the aldehyde, the ketone, the carboxylic acid, the ester, and the amide. The C double bond O group by itself is called a carbonyl group. And so you would call these carbonyl containing functional groups, as are these ones farther below too. So that's just to work, just so you're familiarized with what you want to focus on out of this table, which is a real useful table because it has some of the naming, the suffixes, the name endings, and an example of simple versions of these functional groups in simple compounds. So beyond recognizing, we want to begin to understand their chemistry. If we look at the space-filling models of electron clouds, remember molecules can be looked at in lots of different ways. The red is where you have highest electron density. High electron density. This is, of course, due to electronegativity. So the oxygen in there, in the alcohol, pulls electron density toward it because it's electronegative, but also it's got those lone pairs. So this red area is probably mostly due to those two lone pairs. So we know about structure. We want to start thinking about structure in this way, in many different ways, really. Again, this ether has two lone pairs there, so it's most red there. These things are going to start to influence the reactivity of these. So these are that collection of sp3 hybridized functional groups that I pointed out in the last video. So they're all going to be roughly tetrahedral and single bonded all around, or lone pairs. Taking a more detailed look, say, of an alcohol group, it's important to start to understand that, yes, electron density is high here, but you also have polarization. So delta minus on the oxygen, delta plus on the carbon that the oxygen's attached to right there. That's polarization due to polarity, however you want to say it, polarization. It's sort of, that's a description of the phenomenon we're seeing. Inductive effects are more like a verb that comes from a polarized part of a molecule or set of atoms. So the oxygen atom is pulling electron density in this direction, creating the dipole, the polarization. But the way that this whole thing behaves with another atom or molecule coming in, we would talk about as inductive effects. So if you had some sort of atom coming in that was, say, negatively charged. So I'll just call it a generic base for now. It's not really the best thing to use, but a Lewis base, an electron pair donor, might be most drawn, or these electrons might be most drawn toward that partial positive charge. We would call that inductive effects. We would describe it like inductive effects lead to the base attacking the carbon of the alcohol. Now, typically you need a little bit more for this actual reaction to occur. If we look at a carbonyl containing functional group, and we have a base, I'll just again use a generic, something with electrons, Lewis base, electron pair donor. Then we could say that this base, due to inductive effects, might form a bond to that carbon. It is more likely to happen in this case with a ketone than with an alcohol. This is polarized as well in the same way, but in this case you can have a bond forming and displacing electrons of one of these covalent bonds toward the more electronegative oxygen. Remember, these are just pairs of electrons being shared. And so this allows for a reaction like that to occur more readily than the alcohol version of this that I showed. So the result of those two arrows, this is bond breaking, is when that bond breaks, it ends up as a lone pair, and we have a new bond here to what we just called B in this case. So this is how functional groups can work to affect reactions. Some of the keywords: polarization, inductive effects, Lewis base. So if we look at amines, another sp3 hybridized functional group, and by the way, we're going to study those kinds of reactions with carbonyls much later in the organic sequence. So here's an amine. I don't know, we'll just put it like this. If we react this amine with something like aqueous acid. So aqueous acids, no matter what they are, if they're hydrochloric acid, sulfuric acid, phosphoric acid, whatever, since they're aqueous, they typically will form an active species we call the hydronium ion. Should be familiar from general chemistry. And we should be able to predict, based on our knowledge of all of this kind of stuff, that the lone pair on nitrogen is a Lewis base, electron pair donor, a region of high electron density. Yes, this is polarized, delta minus, delta plus, but in this case, it's the delta minus that's reacting, forming a bond to a hydrogen. displacing electrons away from that hydrogen toward the full plus charge. They certainly want to go toward a full plus charge, negative to positive. The result of those arrows, those two arrows, will be that the amine nitrogen then picks up another hydrogen using that lone pair. It is now a plus formal charge, and then the hydronium ion is, technically we would say, oxidized to water. And so the hydronium ion is a Lewis acid, an electron pair acceptor. Right? Because that's exactly what it did. It accepted, just because it's accepting electron pairs from itself doesn't mean it's not an electron pair acceptor. Okay, so all of these functional groups that you see above here, the oxygen, the nitrogen, the sulfur, all these sp3 hybridized functional groups, they can all react in very similar ways to the example I just showed you. With acid, and with base, something like, something like your SH, for example. Maybe I'll make this a ring to keep it interesting. So with a base, like an OH minus, with its 3 lone pairs, 2 lone pairs on sulfur if you want to draw everything in. A base, the above reaction won't happen. This sulfur isn't likely to pull electrons, pull a hydrogen off of an OH minus already. That would make the O actually -2 if you think about it. So in this case, that can't happen. The only thing that can happen here is that the Lewis base OH minus can pluck a proton off of here, displacing these electrons onto the electronegative sulfur atom. And the result of those arrows would be now a negatively charged sulfur with 3 lone pairs. You see why formal charges are so critical, to not have to sit and calculate slowly every time. The OH picks up another hydrogen, leading to a neutral water molecule. No formal charge here. So this is your Lewis base electron pair donor. This is your Lewis acid electron pair acceptor. Again, accepting a pair of electrons from itself still counts. So this is just a beginning to all the functional group reaction chemistry that we're going to need to know eventually. Back to just, you want to be able to recognize functional groups within larger molecules. So don't be, daunted by the size of molecules. A lot of times we're just focused on certain parts of them, or even a very small part of them, and the rest is just hanging on. So in this case, this is the molecule Taxol that I showed in in-person class this week. And if we want to identify these functional groups, there we have an amide, an alcohol, an ether, see, attached to carbon and another carbon, ether, not ester, another alcohol, a ketone, not ketone. If you write ketone, automatic F for the course. So this is an ester. You can tell that bothers me, right? Another thing to point out is we do differentiate between alcohols and amines of different types. We'll get into that in the next video. This alcohol here is attached to 2 other carbons. And what we're really looking at is the carbon of the alcohol is attached to 2 other carbons. That's a secondary alcohol. This alcohol carbon is attached to 3 other carbons and is called a tertiary alcohol. So we're going to get into that more, and amines have a similar nomenclature. Here's another molecule, dinomycin, another cancer drug. Well, this one never made it to past the clinic because of toxicity. But it has a really interesting structure and lots of functional groups. So here we have an alcohol. But even this has a special name that we won't go into right now. Well, I'll just mention it. It's actually a phenol. It's like a special version of an alcohol because it's attached to the benzene ring. Here's a ketone, an amine, and that's a secondary amine because it's attached to 2 other carbons. Alkynes, we know. Alkyne. Here's a carboxylic acid. And notice this is an ether. So I'm going to stop there. We're going to go more into the different kinds of chemistry and nomenclature of functional groups, including arrow pushing stuff as we go along.